In the first video of this unit, we took a look at, in part at least, what current does in a circuit. So we defined current and traced its path in a circuit with lamps and a capacitor. And now I want to take a look at the voltage. Voltage is another very important physical quantity. And you may or may not have the background, but it's defined as the energy per charge. Basically, the charge that flows in a circuit, how much energy those charges have, is what we mean by voltage. So it's a simple definition, but it's a little bit abstract concept at the same time. All right, so here's a circuit, and we have a 120 volt power supply. And we got three resistors, 30, 10, and 20. And as you can see, current can flow around this whole thing because there's a complete loop with those circuit elements. All right. And now, what we have here, as you can imagine, the more resistance we have, the more it restricts the flow of charge. So the current is going to be inversely proportional to the resistance. That makes sense, right? More resistance, less current. But what I want to do here first is, before quantifying that a little more, is to say that this 120 volts, that's the charge pump. It's like a rise in elevation for a waterfall. And then the resistors are like drops in the elevation. So it drops across a 30 ohm resistor. There's a plus to minus, a voltage drop across each one of these, the 10 and the 20, plus to minus. It's like this side is higher than the other side. Okay. The V, the voltage, across the whole, for the whole circuit, basically this 120 volts, is the V of the 30 ohm resistor plus the 10 plus the 20. And that's 120 volts. So so basically, what is not seen here necessarily, obviously, but what I want to tell you it is that these are drops across each of those resistors, and they equal to the rise of the power supply. Now, if you don't know this already, you will from the Ohm's Law lab, which we'll be analyzing next anyway. The circuit resistance, R, is equal to V over I. And if I had just mentioned previously and intuitively, if we solve for I, put I over here, then I is equal to V divided by R, bring R down here. So the current is greater, proportional to the voltage, inversely proportional to the resistance. So that's intuitively pleasing, I hope. But resistance now is also then solved for as V over I. Okay. And that's volts over amps, and the symbol for that is ohms. That's the unit. There's the typical symbol, capital omega. Now, since voltage is energy per charge, I'm showing that as electric potential energy of the charges divided by the charge. So the quantity of charge. So how much energy the charges have. That's a measure of the voltage. And we're going to go progressively, spatially, work across here and graph a plot of this energy per charge, or voltage. So to start with, across the 120 volts, our reference for 0 is down here, or at this point on the negative side. No, we're going to call that 0. And it rises 120 volts. And along a conductor, it doesn't change. So we're going to progress along the conductor at the same voltage. And now we get to this, as we look at this resistor, it drops across the resistor. So spatially, across that region, there's a drop in the energy of the charges. And then in like manner, we move to the next resistor, and it drops across there. Of course, less, because it's only a 10 ohm, whereas this was a 30 ohm. And then again, maintain till we get to the 20 ohm resistor, and then that drops down all the way down to the potential of the negative plate, same as over here. This is all a single conductor, and there's no further drops in the conductor, all the way down to the 0 point. Like if this was a waterfall, get the water to the top of the mountain, and it flows down various hills. And now if we want the circuit to continue to flow current, we have to bring this back bring these charges back to get pumped up by the power supply again. So that's the basic idea. And as I've already mentioned, now we'll put it in writing. In any circuit, the sum of the voltage rises, in this case that's the 120 volts, that's it, is equal to the sum of all the drops that we have in the circuit. So the sum of the voltage drops. So in expressed mathematically, this is the sum of the voltage rises equals the sum of the voltage drops. And the reason that's fundamentally important because it is consistent with a law of nature known as the conservation of energy, because we're talking about the energy of the charges. So however much energy is put in can be removed, and when we go around a complete loop of a circuit, it's always the case that the rises and the drops are the same for conservation of energy. Okay, so I want to do another sample circuit to demonstrate the idea of the sum of the rises and some of the drops are the same. And this again will be a demonstration, and yet it's very understandable without necessarily seeing it in action. So here our circuit is the 140 volt power supply. Current flowing around the circuit and back. Charges get pumped up after they lose energy across the components. Now, the total resistance, you just add them up. 10 and 20 and 40 gives us 70 ohms. The current, if you picked up on it, the current is proportional to the voltage, this, inversely proportional to the resistance. So basically, and it's, in fact, it's equal to those things, not just proportional. So it's 140 divided by 70. So that is 2 amps. That's the current flowing in the circuit. What I want to specify now is the voltages at various points. But voltage is always measured with respect to something. So when we say, for instance, that the voltage at B is 140 volts, what we implicitly mean is that it's with respect to point A. In other words, the voltage across the power supply is 140 volts. That's the difference in potential. So my reference potential in this discussion is point A, or you can think of it all along here. This is all at the same potential, and we're going to call that 0 volts. So when we say VAA, what we mean is the voltage of point A with respect to, you got it, point A. In other words, point A is the reference. And of course, that's 0. There's no rise or drop from A to A. It's the same point. So A is the reference point for 0 potential. Now, if you have that basically nailed down, then it's going to be understandable when we say VBA, the voltage of B with respect to A. So what does B look like from the vantage point of A? A is sitting there going, I'm kind of lonely down here. I have no potential. And it looks off into the distance and sees B. B looks like it's a greener grass syndrome. B looks like it's definitely in lush pastures. And A says, B, you look like you're 140 volts more than I do. That's what we mean by the voltage of B from the point of view of A. It's a rise of 140 volts. So there it is. A voltage rise of 140 volts exists as we progress from A to B. Now, if we think of B to C, what's happening? We already know, or hopefully do, you can figure it out if you think about it again, because I've showed you the equation already. The voltage across this, it's a drop. The energy of the charges is reduced as current passes through the resistor. And that that voltage is the current times the resistance. So it's 2 amps times 10 ohms. Well, that's a drop of 20 volts. So it drops. Higher here, lower here. And this can be verified with a voltmeter, as I will do in class. So the voltage of C with respect to A, that's what VCA is. You're at A, you're looking at C. Well, when you were looking at B, you said, hey, here's 140 volts. But if you shift your gaze over to C, you look at C and you realize, oh, from 140 volts, it's dropped 20. So what do you have left? That's right, 140 minus 20, which is 120. That's it. And now, what about from C to D? Is it a rise or a drop? Well, once again, it's a drop. And how much this time? Well, it's 2 amps times 20 ohms, which is 40 volts. So now if you put your probe between D and A, the voltmeter probes, the voltage of D from the point of view of A says, well, it was 140. It dropped 20. Now it dropped another 40. So basically here we saw 120 at C, right? 120 volts at C. But then it drops another 40. So that leaves 80 left. And finally, let's do it one more time. When we traverse D to E, we have another drop. This time, 2 times 40 is 80. So now, at D, we were seeing 80 volts, but then it drops 80 volts. So guess what? VE with respect to A is 0. But that makes sense, because there's E, and E is really the same electrical point as A is. Because along a conductor, there's no resistance, theoretically, and so there's no voltage drop. So they're really at the same point. So what is the sum of the V rises? Well, the V rise was just the single 140 volts. And how about the sum of the V drops? We dropped 20 and 40 and 80. I believe that's 140 volts. In fact, it is. And that validates the point I'm trying to make, which is the rises and the drops. Basically, they're equal. If you say V rise and V drop, you have the same number. V rise you can think of as positive, V drop as negative. So the algebraic sum of the rises, the algebraic sum of the voltages around a circuit really adds up to 0. Does that make sense? Very good. We'll stop the discussion for now, hit some other ideas very soon.